This video is on 6.5 for precalculus, graphs and polar equations. During class, I went through the different symmetries that can occur in polar equations. You could have symmetry in the x-axis, y-axis, or the origin. So if you missed class, you need to take down those notes. You can pause this video and jot that information down. Graphically, here are the graphs. Here are the reflections in each of those different types of symmetry. And algebraically, these are the tests that you can make to see if those occur. So remember, for each of these, if you are testing for symmetry, you're going to replace r and theta with either the first option over here or the second. And then what you're going to do is you're going to see if when you do that, you can simplify your expression back to what you started with. If you can, then you have tested and found that there is whichever symmetry that you were testing for. If you can't, then there isn't that symmetry. And then here was an example that I went through in class, again, in case you were gone. R equals 2 sine 2 theta. That's a polar graph. It is symmetric. We're testing to see if it's symmetric about the y-axis. So when it's the y-axis, as you can see here, you replace r and theta with negative r and negative theta. So that's what I did. Replace the r with a negative r, theta with a negative theta, here and here. And then 2 times negative theta is the same as negative 2 theta. And then if you remember back, sine negative theta is equal to negative sine theta. That was one of our identities from a chapter or two ago. So that means that 2 sine negative 2 theta is the same as negative 2 sine theta, or sine 2 theta, excuse me. And that could be simplified to what we started with by multiplying or dividing both sides by a -1. Since these two statements are equal as proven here, or are equivalent, there is symmetry about the y-axis. Now, there are 4 main types of polar graphs that we'll be discussing in this chapter and that your polar project is going to be about. The first of which is called a rose curve. Now, a rose curve, you need to follow these guidelines here. For a rose curve, you need to have the equation written in one of these two forms, not both. You only need to graph one of these to make a rose curve. So what you need is r equals a cosine n theta, or you could use r equals a sine n theta, where n is an integer greater than 1. So that'd be, n would need to be 2, 3, 4, 5, or so on. Couldn't be 2.5, it couldn't be 3.8, it has to be an integer. So what that means is you're going to plug some number in for a, you're going to plug some integer in for n, and create this rose curve. What you're going to find is, after you experiment with it a little bit, or after you've probably realized that that a value that you use, that's how far out the petals are going. And then how many petals you get will be determined by this n number. That n, if it's odd, there's going to be n number of petals. If it's even, there's going to be 2 times n number of petals. So what you might want to do is you might try to create the graph that I have shown here and see what you can do with it. Some extra information about this graph that I didn't go over on the first day of these notes is the range of values. First of all, the domain is all reals. You can plug any number in for theta and it'll work. The range is going to be the negative absolute value of a to the absolute value of a. It's continuous. If n is even, it's going to be symmetric about all three, the x-axis, the y-axis, and the origin. If n is odd, then r cosine n theta is symmetric about the x-axis, and r sine n theta will be symmetric about the y-axis. So one other thing you'll want to do is you'll want to plug in cosine and sine and see how the graph changes. Now I'll show you a graph of an equation on the graphing calculator. Now, there's a couple things to consider when you're graphing on your calculator. First of all, it depends on what your purpose is for graphing on your calculator. If you're graphing on your calculator to help you graph on your paper, you're probably going to put different settings into your calculator as far as your window goes. If you're graphing on your calculator to try and make it look as accurate as possible, you're going to graph it differently than if you're graphing so that you can get help in graphing on your paper. So what I'm going to do is I'm going to type some things in so that I can graph on my paper more easily. So this graph that's shown on the screen over here on the note page is the graph of 3 sine 4 theta. I knew it was 3 sine 4 theta because there's 8 petals, which means I needed 4 theta. It goes out to 3 units, which is why I use the 3, and then I use the sine function instead of cosine because it didn't come up along the x or y axis, and you'll get used to recognize cosine and sine in that way. So what I want to do for my window setting is I want it to go from 0 to 2 pi for my theta min and max. 0 to 2 pi, so it went around the circle once. I could go out farther if I wanted to. That's not an issue. You could too. My theta step, what I used was I used pi over 12 for my theta step. Now this would not be a good setting if you want it to show up and look good on your calculator. That's too big of a step. However, I picked pi over 12 because what I'm going to want to use is I'm going to want to use the table on the calculator to help me plot some points. If I use pi over 12 for my theta step, well then what I can do is I will plot every pi over 12 points on my graph, and I can go to my table and look at every pi over 12 theta increment and plot the points shown. Why do I want to use that? Well, if I'm using this polar graph setup, then what I'll be able to do, and I'll give you a sheet like this if you haven't got one already, what you can do is all of these lines that are already preset are in increments of pi over 12. We've got 1, 2, 3 pi over 12, 4, 5, 6 pi over 12, 7, 8, 9, 10, 11, 12 pi over 12, which is pi, and so on. So now I'll be able to go to my table on here, and well, first I'd go to my table setting, make sure that I started at theta equaling 0, and then for the change in the table I typed in pi over 12. So then when I go to table, I can plug in these points. At theta is 0.268. Well, I know that's on this first line. I need to go out 2.5981 units, which means it's not going to be perfect, but if I go on this first one out to 2.59 something, I'm plotting a point here, or so. And then for this one, same type of thing, only it's on the next line, it's on the next angle, I should say, I go out the same amount. And so on and so forth. So that, these points that I plot will now give me a somewhat accurate sketch when I'm trying to draw the graph that I know it should look like, which is the graph that we were just looking at. Whoops. The graph that we were just looking at on here. This graph here. So what I just plotted was a point approximately right here and approximately right here. So out a little past 2 units, so it's probably like right here and right here. Just to help me line up where that pedal should go through to make my graph look as accurate as possible. So now what I was saying was the graph on here is not going to look very good, the graph on my graphing calculator, because the theta step is so big. So I'll just show you what it would actually look like. It looks more like a pinwheel than this flower, these nice curves at the ends. But that's okay. Again, it's just meant to graph. It's just meant to get the points that I wanted to graph. That's what I meant to say. So, and it looked pretty neat anyway, like that. I'll throw in cosine here so you can see what this one would look like. This is pretty neat too. Not accurate, but the graph still does look neat. Like a snowflake, maybe you'd think. Or some of you probably would call that a ninja star. Yeah, that works too. Again, it's not accurate. If I change my window setting, instead of pi over 12, maybe I could just put a decimal in, but I like to put in like pi over 24. If I graph that, see how much closer it's getting to what we're trying to accomplish. So keep those in mind when you're graphing. The second type of curve you want to consider is the limacon curve. Limacons need to be written in the form r equals a plus b sine theta, or a minus b sine theta, or a plus b cosine theta, or a minus b cosine theta, where a is greater than 0 and b is greater than 0. Now there's different types of limacons that you can get. You could get a limacon with an inner loop. That will occur when a over b is less than 1. When a over b is less than 1. So when would that occur? Well, if a is smaller than b, that will occur. You could get what we call a cardioid. Looks like this graph. When a over b equals 1. Well, when is a over b going to equal 1? When a and b are the same. You could get a dimpled limacon, like here, when a over b is between 1 and 2. And you could get what we call a convex limacon, when a over b is greater than or equal to 2. For this one, the domain is also all reals. The range is going to go from a minus b to a plus b. It's going to be continuous. There's the symmetries, and so on. I'm not really going to have you analyze the graphs. There's going to be a portion of your homework where it says to do that, but really all I want you to do is like what we were just talking about. I want you to be able to make an accurate graph on paper. So you can use your graphing calculator to help you make an accurate graph on paper. That's what I'm going to be looking for. Not for you to be able to analyze the graphs, but just make an accurate graph on your paper. And be able to manipulate the equations to make these different types of graphs. The third graph is the spiral of Archimedes. That's where r equals theta. Here's the first graph I made. The graph is just r equals theta. You need to start considering, well, why is it only going around the curve that far? You need to think about things like that. Well, if I look at my window, I just went from 0 to 2 pi. If I change that to go from 0 to 4 pi, notice what happens. You go around twice. Well, consider that when you're making your graphs. Also notice on my window setting, I didn't mention this on the last one, what I'm doing is I'm taking multiples for my x min and max, my y min and max. I'm taking multiples of a square window. If you do that, that's going to keep your sketch looking accurate. If you if you change it, if you change the x min and max and the y min and max proportions from what I have here, uh, you're not going to keep that equidistant distance in between the curve, if you will, or the spirals that go out. Also consider uh, what theta values you're using. What if I use negative ones instead? Maybe I want to go from negative 4 pi to 0. Well, what's different about that graph? Things to consider. Um, and maybe those are things that you're going to need to know or look into when you're trying to match your graphs on your polar project. The last graph I'll show you is the lemniscate. R squared equals a squared sine 2 theta, and r squared equals a squared cosine 2 theta. On these, you don't have a variable with the theta. You need to use a 2. The a is what you can change. And then how are you going to graph these? Well, you'll have to take the square root of both sides and then graph the square root of a squared sine 2 theta and graph negative the square root a squared sine 2 theta. You have to graph both of those. So experiment with those, see what you can do, and again, what we're trying to do is get accurate graphs, accurate drawings. And then I'll just leave you with, you can read through this example to help you get another insight into the way your grapher can help you in analyzing different curves. So I'll just kind of scroll down here, and you can pause at different points as you see fit.